Okay, so day 2 of comparing linear, quadratic, and exponential functions, relations, equations, however you want to call it. Um, Today we are going to be comparing rates of change. Okay, very specifically, rate of change is basically like slope, right? That we say in a linear problem. But if it's not a linear function, then you can't call it slope because slope is very specifically only for linear. Okay. So in anything else, you're going to call it an average rate of change or just a rate of change. Okay. So that's the reason why there's two different words for it. So one is specific for linear and one is for anything else. Okay. So we call it a general term, rate of change. Okay. So we're going to be doing this from several different formats, from functions, from tables, from graphs, just like we did on the comparison. Okay, so let's start off with a basic one. Seeing if we can recognize linear, exponential, and quadratic from this. Okay, so you have three choices. And again, it's a question of which one is linear, which one is exponential, and which one is quadratic. Okay, so payment option number one, you get $100 per day for 15 days. If we were to write an equation or function from that, what form do you think this would be? Right? And how much do you think you'd get at the end of 15 days? Okay, so $100 per day for 15 days. Well, that's pretty easy. That's just 15 times 100, right? So your equation would be that. So this is most definitely linear because the X would just be my days and my Y would just be my pay. Okay, and so it's $100 a day for 15 days, linear. Okay, so my second option on day one, I'm going to get $1 squared. And there's your clue of what kind of function it's going to be. On day two, you're going to get $2 squared, which is $4. On day three, you're going to get $3 squared, and you're going to get this pattern for 15 days. Okay, so since it has squared in it, we know it's going to be quadratic. Get a different color. Okay, so that's going to be quadratic. And since I'm not starting off with anything, I could actually still write this as just x squared. And I'm going to get that every single day. So I'd have $1 and then 4 more. So that's 5 and then 9 more. And we'd have to add that all up for 15 days just to see how much we would get. Okay, so the third option, you would get a penny for the first day. On day two, you're going to get 2 pennies. On day three, you're going to get 4 pennies. On day 4, you're going to get 8 pennies. And this pattern continues for 15 days. So what is happening to your pay? If you caught the fact that it was doubling, you are absolutely right. That means that this is exponential because it is being multiplied by 2 every single time. And we did exponentials in unit 4. So your starting amount is 1 penny and 2 for the rate to the x power. Very good. And you're going to do that for 15 days. Now, deeper thought question on this. When would each of these be better? Right? You'd actually have to graph them or get your answers all the way up for 15 days just to see which one is actually going to be better. So let's take a look at the graphs of these just to see if we can see a difference between them. Okay, so this is for 15 days right here.
Unknown caller.
Okay, so I'll mark it just so you can see it. This is the 15-day mark right here. Okay, so at 15 days, at the end of 15 days, which one is your better option? The linear, that's right, because it's higher. So this is the better option. And in this case, it basically means that you're going to have more money. Now, take a look at the green function compared to the blue one, right? You get to a certain point and take a look. That green one, that exponential, is actually going to be higher than the linear function. So that looks like about, say, somewhere between day 17 and day 18, maybe. So we'll say between day 17 to day 18, the exponential is actually going to make you more money. Now, if you take a look at the red one, okay, the red one is eventually going to curve up, right? It is quadratic. That is what it's going to do, but it's going to take a lot longer for the quadratic to catch up with the linear that you have. Okay, so all of this is basically, again, it's another comparison, but it is something that I want you to understand that eventually, okay, and I don't mean at the very beginning, obviously, eventually, an exponential is always going to get bigger. You could have said that you were making $1,000 a day on there and still be doing the penny times 2 every day for the exponential. Leaving out words, is always going to get bigger. Okay, just because of the way exponential functions work, even if you were making $1,000 or $10,000 a day on the linear function, eventually the exponential function is going to get bigger, period. Okay, so if you're ever asked, if you're ever shown 3 functions or on a graph or anything like that, and you're asked which one is eventually going to be the biggest, the answer is always the exponential. And in fact, had we gone for 30 days instead of 15 days, little hint, if you're ever offered this as a choice, this exponential function will actually give you more than $1 million at the end of the month. Right? At the end of 30 days on the linear making $100 a day, you'd only make 30,000, right? $30,000. The exponential, you would end up with more than $1 million just because of the way it grows. So yeah, exponential is always going to get bigger eventually. Okay, so back to our comparison by rate of change. So we have a formula, very specific. We've done it before when we were doing linear functions. The rate of change is the difference between 2 y values, right? It's always just 2, divided by the difference in 2 x values. Okay, so you have to have 2 points to do this, right? So the formula, and again, very, very familiar, is y2 minus y1 over x2 minus x1. And that's just our basic slope formula, right? That's really what it is. The average rate of change is the same thing as slope. It's just that slope is only for linear. Okay, so I can give you 2 points. I can give you a graph. I can give you a table. I can give you all this different information, and you should be able to find the slope or average rate of change given that information. So let's get some practice. All right, so let's start with a graph. Okay, so let's do the linear or the red one first. So I can take any 2 points, any 2 ordered pairs that are on my linear graph, and it doesn't matter which 2. It doesn't even have to be the ones that I have marked. It could be anything as long as it's a whole number, right? You wouldn't want to pick something like here that would be in the middle of a box, right? Which would give you some kind of unknown fraction. So we always want to pick the whole numbers. All right, so I'm going to choose this one, which is the 0.10, and this one, which is the 0.23. Okay, and I'm going to substitute those into my formula. Okay, so the second y value, we're going to call the second y value the 3, right? That's y2, and that's y1. So 3 minus 0, and that has to be x2 and x1 over 2 minus 1. Okay, so that is basically 3 divided by 1. So this has a rate of change of 3. All right, so let's try our exponential. And again, picking 2 whole number points just to see what the average rate of change is. Now, interesting statement on this. With the linear one, what we saw yesterday with the differences is that your rate of change, right, your y value difference is always going to be the same no matter what points you pick. Depending on what points I pick on my exponential, I'm going to get a different rate of change. Okay, so I could pick these 2 points down here, or these two, or those two, or even the top to the bottom. Okay, but you're going to be told which points to use. So I'm going to tell you right now, we're going to use 2, 3, 4, 5, 6, 7, 5. Okay, so 7, 5, and 2, 3, 5, negative 1. So I'm going to let you know that we would do the points 5, negative 1, and 7, 5. And sometimes you'll only be given the x value. So I could tell you what is the average rate of change for x equaling 5 to x equaling 7, and you would go find the points that go with that. Okay? Again, same formula. We're just going to substitute it in. All right, so that's going to be y2, which is 5, minus y1, which is negative 1. So minus negative 1. We do have a double negative there. Okay, divided by x2 minus x1. So that's 7 minus 5. Okay, so 5 minus negative 1 is 6. 7 minus 5 is 2. So that one from those 2 points also has a rate of change of 3. And again, if I picked 2 other points, I would get a different rate of change, right? Because it does curve. So the slope is not the same every single time. All right, so let's try the quadratic one. And again, this is just what you'll be expected to do given 2 specific points on a graph, find the rate of change. All right, so got this one, 1, 2, 3, 4, 5, 6, 3. So that's negative 6, 3. And how about this one? 1, 2, 3, 4, 5, negative 1. And again, if I picked 2 other points, the top and the bottom, or the bottom and the middle one, I would get a different rate of change. This is how this works. So y2 minus y1, 3 minus negative 1, and then x2 minus x1, and that's a negative 5, negative 6 minus negative 5. So 3 minus negative 1 is 4. 6 minus negative 5 is negative 1. We do need to simplify that. That's going to be negative 4. So that has a rate of change from those 2 points of negative 4. Again, this is how we do this from a graph specifically. Okay. All right, so let's try from, what we got next? Yes. Okay. So let's try from a function. And when you're given a function, you have to be told which 2 values you are using. So like on a graph, again, you'll be told which 2 points and you can get the visual and you can write your ordered pairs down. On a function, it takes just a little bit more work. So let me show you how this works. Okay. This is my interval. All right. Very specific, very important definition when we talk about this. An interval. This is very similar to how we write domain and increasing and decreasing, right? We write it over a specific value. These are both x's, right? This is not an ordered pair. This is a specific set of x's that they want you to use. First one being x1 and the second one being x2. Okay, so you have to substitute, right, to get your x, or to get your y values rather, to get your ordered pairs, and then you will actually use your rate of change formula. But right now you do not have ordered pairs. What you have is 2 x values that you're being told to use. So I want to know what my rate of change is when x is 1 to x equaling 4. All right, so we're just going to substitute them in one at a time. So if I substitute in 1, 3 times 1 plus 4, I get 7. So my first ordered pair is 1, 7. I substituted in 1, I got out 7. My second one, I have to substitute in 4. And for that one, I should get 16. So my second ordered pair is 4, 16. Okay, so I now have my 2 ordered pairs. Now I can use my slope or my average rate of change formula like we did on the graphs. Okay, but you see first, right, I had to substitute in my x values, that interval that they gave me, and get the y values that go with it. So now I have x1, y1, and x2, y2. And I can substitute those into my formula. So 16 minus 7 divided by 4 minus 1. So 16 minus 7 is 9. 4 minus 1 is 3. We need to simplify that. My rate of change is 3. Okay, so let's do this for something that we know is quadratic. Same thing, we're going to substitute in 1 and 4. So I want the same interval. So 1 minus 4 squared plus 1. And again, very, very, very important to do your order of operations. Simplify what's in your parentheses first, then square it, then add 1. So that's negative 3. Don't forget that when you square a negative, you get a positive. So this should equal 10. So my first ordered pair is 1 and then 10. Right? 1 minus 4 is negative 3. Negative 3 squared is 9, plus 1 is 10. All right, so let's try the next one. Okay, so 4 minus 4 is 0. 0 squared is 0, plus 1 is 1. So my second ordered pair is 4, 1. And again, x1, y1, x2, y2, because that was the order of the interval that they gave us. That x1 has to be the 1, and your second point, the x2, has to be 4. All right, time to plug and chug. So 1 minus 10 divided by 4 minus 1. You got to make sure you're going in the correct direction. So y2 minus y1, x2 minus x1. So that is going to be negative 9 over 3. Simplified is negative 3. So my rate of change is negative 3. All right, last, let's go ahead and do an exponential one. Again, using that same interval, 1 to 4. I'm going to substitute in, right? I'm going to plug and chug so that I can get my y values that I need. So let's start with 1. So 1/3 times 2 to the first power. And that is going to equal 2/3. And I would prefer if you use the fractions instead of the decimals, only because you're not going to get an exact answer if you're trying to do 0.6 repeating. It just doesn't work. So my first point is 1 2/3. All right, so the next one, I'm substituting in 4. And that is going to equal 16/3. And again, much prefer if you use the actual fractions. You will get a much better answer when you are done. So, and your calculator is very capable of doing fractions if you are a little bit struggling with that. So y2 minus y1 divided by x2 minus x1. All right, so that is going to be 14/3 divided by 3. And again, if you put that in your calculator, use a, stacked fraction. 14/3 divided by 3, or used 14/3 divided by 3 as a horizontal fraction, so you can put it in your calculator like this. And that works as well. Should come out to 14/9. And again, leave the fractions the way they are. They're much easier to work with, and they're much more exact this way. Instead of trying to do repeating decimals, you're not going to get your right answers. Okay, so that's it. That's how we compared using average rate of change. So you'll be doing this from graphs, from tables, and from functions. Want to give you a quick example of what it would look like on a table, just so that there is no confusion. Okay, so any values, doesn't matter. We're just substituting them in right now. But if you're given a table of values and you're going to find the average rate of change, again, I have to give you some kind of interval to use. Okay, so in this case, I'm going to say on the interval, rather on the x interval specifically, and I'm going to say from 2 to 8. Okay. And again, if you have the table, this is actually a little bit easier than the functions because I'm telling you which x values I want. So I want this ordered pair, the 2, and this ordered pair, the 8. Okay. This becomes my x1, y1. This becomes my x2, y2, and it goes straight in the formula. So negative 10 minus 5 over 8 minus 2. So that would be negative 15 over 6. That can be reduced. We should try to simplify our fractions as much as possible. That should be negative 5 over 3. All right, and that is how that is going to work. And after this, we'll be doing a whole lot of applied functions since you've learned how to graph and work with linear, exponential, and quadratic. So see you next time.